Okay, hi guys. So this is our new section. It's carrying on with chemistry, and it's called reactions in aqueous solutions. So, or not aqueous solution, but solutions. We are going to also look at precipitates, which means they cannot dissolve in a solution. So, what we're first looking at here is ionic compounds and how they dissolve in water. Okay, so some ionic compounds dissolve in water, such as a salt, or such as salt. So we know salt is NaCl. Remember, we have many different types of salts. It's not only NaCl. So if we draw, now we know that Na is a cation, okay, and we know that Cl is an anion, right? And because they are ionically bonded. So what happens now is water molecules, when you put salt in water, the water molecules have a strong bond between them, and they can actually break apart the NaCl salt crystals. So you know this because you have dissolved salt before. Okay, so what happens is we know that, let me just draw you a water molecule over here. So we know water looks like this. Okay, and remember we have the electronegativities, and the oxygen pulls on the electrons more than the hydrogens, leaving only one proton at the bottom here, which makes the water slightly positive. Now, you haven't seen this symbol before with me yet. It's like an S that attaches its tail to itself. It's actually a small letter delta. Greek letter. We use a lot of Greek letters in science, and we put a little plus there, and that's to say that this side of the molecule is positive, but it's still not a charged particle. It's just that this side of it is now positive, and we know that there are electrons on this side. If we draw the Lewis structure, you'll remember that there are lone pairs here, and so that makes this side of the water molecule negative. Okay, so we know that we have a negative and positive. So what happens here is that this is positively charged, and it will attract the negative sides of the water molecules. Okay, so we'll have oxygen and hydrogen. Let's put it like that. And we know that this is negative. And all the way around, sorry, I should have given a bit more space here, I suppose, hey? You're going to have the oxygen side attracted to the positively charged sodium. Okay, so that's how it's going to look. Let's put another one here so it's fully surrounded. Okay, and that is what the water is busy doing around the sodium ion and all the sodium ions. Now, the chlorine ions, we know that the positive side would be attracted. So that means that our, oh gosh, that's a terrible drawing. That means our hydrogen side is attracted to it. And so we're going to draw it like that. Okay, so if you answer a question like this, make sure that you put which side's positive, which side's negative of your water molecule. So draw it like this. You don't have to draw a hell of a lot like we did with sodium over there, like this, and this one's fine. Okay, so we can see that our positive side of our water molecules are surrounding our negative one because they're attracted to each other. Okay, and that is how the water separates the ionic compounds and dissolves them or dissociates them. Okay, so if we fill in the words now, I don't know why I did this, but all these words pretty much mean the same. We've got dissociation, which is specifically for ionic substances, and then dissolving and dissolution is the same word, same meaning. It's both dissolving and that. So let's just put dissolving here. So because remember, dissolving doesn't necessarily mean you're breaking things up into ions all the time. I mean, you can break up you can dissolve sugar in water, and sugar is not an ionic substance, so it doesn't break up into ions in water. Okay, so dissolving or dissolution is the process whereby water molecules attract ions of an ionic compound, causing the ions to separate, and this is called dissociation. So dissociation is specifically used, the word dissociation is specifically used to separate ions. Okay, so here I'm going to show you an equation of what it would look like if we had KCl and we dissolve it in water. Now, be careful of this. Equations generally indicate a chemical change, okay? So something reacts with something, give you something new. This, however, is a physical change. We are just dissolving the KCl. We had K and Cl ions before. We're going to have K and Cl ions after. They're just going to be separated, okay? So it's a physical change, and you can undo this by evaporating the water. So the only way we're going to do this, I don't know why I do my K's like that. It's very weird. Okay, is we don't show another reactant with it. But what we do is we put water as a little thing above the arrow. We make the arrow a bit longer. And so I'm not showing you that it's being added to water because it's not reacting with the water. It's just being dissolved by the water. Okay, and then what happens in the water is that we separate our ions. Okay, so there it is there. Let me just do that one there as well. Okay, I'm trying to get in the habit of doing that out like that. Okay, so this just shows the dissociation of KCl in water. So that's how you would do and this is not a chemical equation, it's an equation to show you the dissociation of ions in water. It's not a chemical reaction, it is a physical process, and it can be undone. All right, easily. So NaNO3, I know this seems a bit silly with all the chemistry you've been doing, but oh gosh, no, I'm busy talking while I'm doing this. So but it's really important that you understand this part. Okay, so this is Na plus NO3 minus. Okay, K calcium chloride in water, and we get Ka. Now remember your charges, so this would be a 2 plus 2 Cl minuses. Now why did I do that? Remember, this molecule or this ionic compound has, for every 1 calcium, it's got 2 chlorines attached to it. So when the water dissociated, when it pulls the ions apart, it will pull off 2 chloride ions, okay? And so there we have 2 chlorines. So that's why we have to look at this as well. Okay, now we get sodium carbonate in water, and we get 2Na plus CO3 2 minus. We always put the negatives afterwards. I sometimes forget and put it in the front. Okay, so it's not a big deal. All right, so again, this ionic compound has 2 sodiums for every carbonate polyatomic ion, and so when the water pulls it apart, it will break up into its ions. Girls, please, I know you see this, but you've got to know your polyatomic ions so well that you recognize this as a polyatomic ion and not just a C and an O, and don't break up your C and your O3. This exists as a polyatomic ion now. Okay, so be careful about this. This is why you really have to make sure you know your polyatomic ions off by heart. So I want you to do Think Tank 1 first, but I'm going to carry on with the notes, and you're going to do this on today, which is Tuesday, and then you're going to do this activity tomorrow, which is Wednesday, plus a little task. So I'm just going to test you a little bit on what you do in Think Tank 1 tomorrow in a quick quiz. All right, tomorrow. I'm sorry I haven't marked your stuff yet. I've just been trying to set all those assessments. Okay, I'll do it as soon as possible. All right, electrolytes and electrical conductivity. So an electrolyte is an aqueous solution, okay? An aqueous solution, and a solution is always something dissolved in water that can conduct electricity, okay? So that is what an electrolyte is. We often say, oh, if you drop your hairdryer in the bath while you're in the bath, you're going to be electrocuted. That is 100% correct, because you put bubble bath in it and you're creating ions in the water. You also know that the tap water has all these ions in it. They put fluorine and chlorine ions, and so that's why tap water can conduct electricity. But pure H2O, deionized H2O, cannot conduct electricity. There are no ions, okay? So remember, electricity is the movement of charges, okay? So ions are charges, aren't they? They are charged particles. So if we have ions in a solution, we have charges that can move. So that's where the link to electricity comes from. Electricity is moving charges. Ions are charged particles, and they can move in a solution, okay? Where can they not move? They cannot move when they are still stuck in their crystal form, okay, like NaCl. So positive, negative, positive, negative, positive, negative. So if they're in their crystal lattice state, they can't move. So you can't conduct electricity in solid salt. But what you can do is you can melt it so that it becomes liquid, or you can dissolve it in water. You can make it a solution. Oh, my cat is here. Oh, sorry guys. I have to I'll put some stuff on his bed on my desk. Okay, so substance which can become ions in water are salts, acids, and bases. We will do acids and bases in later on this year, but we're going to do it more extensively in matric, okay? So when salts, acids, and bases dissolve in water, they are considered electrolytes. Okay, so factors that can affect the conductivity of solutions. So some solutions conduct electricity more than others. So these are the factors that assist this. So obviously the nature of the substance. So some substances dissociate into ions and some dissolve as molecules. Okay, so for example, like I said, sugar. Oh, sorry, my cat is busy loving me at the moment. Sugar dissolves in water, but it doesn't break up into ions, it breaks up into molecules. Okay, and it can't conduct electricity if it's in pure H2O, okay? It will break up into molecules, so that doesn't conduct electricity. So if they dissolve as molecules, they are not charged. So what other substances could dissolve as molecules? It's covalently bonded molecules, okay? Most of your ionic solutions compounds can dissolve. Solubility of electrolytes. So some substances dissociate more than others, okay? And I'm going to show you this as well. More ions, more conductive, okay? So some substances dissolve more than others. The concentration of solution, obviously, if I have salt, water, and I put a teaspoon in a liter, or I put a cup in a liter and I dissolve it, the salt solution with the cup of salt in water is going to conduct electricity much better than the one with a teaspoon of salt. Okay, the temperature of solution. Now you would think that all solutions would dissociate or dissolve better in hot water, but that's not the case. It depends on the substance. So some substances just dissolve in colder temperatures much better than warmer temperatures. So be careful about not saying warm temperatures, just say different temperatures. So different substances can dissociate better in different temperatures, okay? Generally, it's hot temperatures. We know that from dissolving things. But there are substances that actually dissociate better in cooler temperatures. Okay, so this is the next exercise I'd like you to do. This one you can do tomorrow or Wednesday, and after your task. Okay, I'm really going to make it a quick multiple choice task so that you don't have to stress about it. All right, girls. Okay, have a good day.